Hello everyone, in this video I will present a paper I co-authored entitled Using Agents and Unsupervised Learning for Counting Objects in Images with Spatial Organization. This work is part of a project going on between ICAART21 and Terranovia, carried out by the Equinox team. Don't hesitate to contact us if you have any questions. Also, you may find a link to the paper and the poster related to this video in the description below. This video is divided in 4 parts, describing the problem, the method, the datasets, and the results. Methodologies tackling the issue of object detection in images have made tremendous progress in the last 2 decades. With this paper, we investigate the case where objects are not randomly positioned in images, but spatially organized. Typically, this is the case of cars in a parking, items in the shelves of a retail store, seats in stadium or conference halls, plants in crop fields. To detect objects that are in this situation, our method relies on 2 steps. In the first one, the spatial organization is approximated using unsupervised learning. In the second step, a multi-agent system is initialized based on the approximation and refines the detection of the objects. We use the detection of plants in crop fields as a case study, but we argue that the framework of our method should also apply to the other examples previously mentioned. Let's start with some image preprocessing. We use the Eliott segmentation based on the excess green index to identify the areas of an image that most likely contain the target plants. This is a pretty common step that can be found in many other works on plant counting. Then, we make sure to rotate every image so that the rows are vertically aligned. This can be achieved in different ways, one of which is suggested in the paper. Once done, here comes the real approximation step. We begin by looking for the crop rows. The Eliott images are binary images with white pixels indicating either crops or wrongly segmented weeds. But, since the crop rows are vertically oriented, if we project the white pixels on the x-axis and make a histogram out of the projection, the position of the crop rows should appear quite clearly. Let's try it out. The resulting histogram has an obvious periodic nature, and, for any crop field that is not infested with weed, the spikes of this histogram should correspond to the visible crop rows. Then, as the signal is periodic, we perform a Fourier analysis to compute the main frequency of the signal which, in turn, gives the inter-rows distance. With this, it is not far-fetched to find the actual position of the crop rows. We proceed in a similar fashion to estimate the position of the plants. For each row, we indeed start by building a histogram, but this time we do so on the y-axis. We repeat the Fourier analysis step, from which we extract the main frequency of the signal that yields an approximation of the interplant distance. This overall approximation can either get very accurate or very bad estimation of the number of plants. But, even for bad counting cases, the position of the plants that it manages to compute are enough to initialize the second step of our method. We use a multi-agent system to refine the approximation of the spatial organization. The system is based on a classic corporate hierarchy with 4 layers. At the top, we find the director agent. Its main role is to start and to decide when to stop the refinement. Then, we have the row agents. The director instantiates as many as the number of detected rows during the approximation step by the Fourier analysis. The third layer contains the plant agents. Groups of plant agents are instantiated under the command of each row agent. Similarly to the row agents, there is initially as many plant agents as the number of detected plants during the approximation step. Finally, there are the pixel agents. Groups of pixel agents are supervised by each plant agent. The top 3 layers are working in order to refine the spatial organization, while the bottom layer senses the image. At the end of the refinement, we wish for the number of plant agents to equal the number of target plant visible on the image. To that end, row agents can adjust the number of plant agents it commands along the refinement process. The adjustment is done relatively to the interplant critical distance, or for short IPCD, computed by the director agent. A row agent can indeed initialize new plant agents in between 2 PAs that are considered too far apart. On the other hand, 2 PAs within the same row can be merged if they are considered too close to each other. To improve the accuracy of the detected crops, PAs are given the possibility to move during the refinement process. Their movements are guided by the pixel agents toward the white pixels. Overall, the simulation is a simple repetition of move, initialize, merge, and destroy. It keeps on going until the number of PAs is stabilized. We relied on synthetic datasets to overcome the lack of public labeled datasets of crop fields. Synthetic datasets are completely artificial and produced by computer means. In our case, we built a procedural crop field generator with the game engine Unity. With this generator, the user can change plenty of parameters to generate crop fields that match his requirements. Once the fields are generated, we simulate the flight of a UAV and capture images at regular points. Beyond the amount of data we can very quickly generate with this system, one big advantage is the complete control that the user has. With synthetic datasets, it is indeed possible to account for a wide variety of cases, which might be hard to come across in real datasets. As such, we use synthetic datasets to design the core of the method, but also to effectively test it. We indeed noticed, in other works on plant counting, that the performances of state-of-the-art methods is highly dependent on how much the target plants overlap with each other. Plant overlapping happens as the plants grow, so this suggests that the current methods have troubles to count plants that are at a late growth stage. To test how our method fared regarding plant overlapping, we generated synthetic datasets corresponding to the three main situations. In each dataset, we generated 100 fields with the plant density of 7 plants per meter square. This much is common for sunflower fields, for instance. For each 3 datasets, we computed the average counting accuracy over the 100 crop fields, and the results on these are very good. They are so good that one could actually wonder if the synthetic nature of the images did not somehow make the detection task easier. So, in addition to the synthetic datasets, we labeled 50 real images of a crop field. The images were randomly selected and labeled from a dataset of over 2,000. While looking at the real dataset, we found that it contained images comparable to the one in the synthetic datasets, if not more difficult. In any case, here too the average counting accuracy was high despite the standard deviation being wider than the tests on the synthetic datasets. Because of the absence of standardized datasets in the field of plant counting, it is rather hard to objectively situate our work in the pool of already existing methods. However, for paper discussing the problem of plant overlapping, we could find mention of error rates. It is around 5% or below when the plants are well separated, and it is around 20% when the plants are overlapping. To our knowledge, our method is also the only unsupervised approach that has such good results. Thus, it is fair to consider that our method stands in the leading group on the problem of plant counting. In this work, we built a method aiming at counting objects that are spatially organized in images. The method is based on 2 steps involving unsupervised learning and a multi-agent system. It was designed using synthetic datasets and further tested with another batch of synthetic datasets as well as real images. In both cases, the method seems to be on par or to fare higher than state-of-the-art methods. Although we use plant counting as a case study, the framework of the method should also apply to other geometries as long as it is correctly implemented in the multi-agent system.